All right. Well, good evening, graduate UNSY students. First, for everybody's awareness, we are now recording this session. A copy is going to be made available for those who are unable to attend live. Next, for the format of tonight's meeting, I'm going to start by introducing our guest, who will discuss his connection to uncrewed maritime system technology. After, I'm going to lead a series of introductory questions, and then we'll open it up to class-wide Q&A. I do ask you keep your mics muted, save all your questions to the end, and that you use the hand raise icon to indicate when you do have a question. I will call upon each of you in order. I also want to note that I'll be capturing and sharing online links to important concepts, details, and tools that are brought up in our discussion tonight. So if you see me on my iPad as we're talking, I'm out there trying to find these links that I'm then going to post into the discussion that'll kind of help connect you to the deeper information that we talk about. So with that, I am thrilled to welcome you to the 22nd session of the UNSY Guest Speaker Series, the first of 3 for this term. I'm Dr. Brent Terwilliger, the program coordinator for the Master of Science in Unmanned Systems degree. Tonight, we are joined by our guest subject matter expert, Dr. John Yamokoski. Dr. Yamokoski has served as Nauticus Chief Technology Officer since August 2022. Before his current role, he served in several other positions at Nauticus Robotics. From 2020 to 2022, John was the Vice President of Defense Technology and Sponsored Research, where he served as Principal Investigator on Nauticus's defense projects and also organized capture teams for new research opportunities. From 2015 to 2020, he was Principal Robotics Engineer. In that role, he was a project manager for technology programs, as well as the director of software for the company from 2018 to 2020. Before joining Nauticus, Dr. Yamokoski was a robotics researcher at NASA's Software, Robotics, and Simulation Systems division at the Johnson Space Center from 2010 to 2015. While at NASA, he led engineering and research teams for control system development of NASA's Robonaut 2 project and the software architecture and development of the Valkyrie program. He earned a BS degree in mechanical engineering from Purdue University in 1999 and MS and PhDs in mechanical engineering from the University of Florida in 2005 and 2009, respectively. And with that, I would like to turn the stage over to Dr. Yamokoski to tell us about Nauticus Robotics, as well as his experience and observations associated with this rapidly changing technology.
Awesome. Thank you. Very thorough introduction. I appreciate that. It's a pleasure to be able to speak with you all tonight. And I'm, I have some material here. It's certainly not technical in nature. Lots of videos. But I'm most looking forward to the discussion and questions at the end. So looking forward to that. So as mentioned, I think in the introduction, I have a very strong background in both space and sea and ocean-going robotics, and titled my presentation here "From Space to Sea." And I think that there's, as you'll see, there's a lot of carryover, especially when it comes to things like autonomous systems that come to play here. So without any further ado, I'll kind of get started. So starting kind of going back in time a little bit and where I originally came from, after graduating from school, a bunch of us, so where we came from as a company, Nauticus Robotics, this kind of from space to sea is really prevalent in a lot of the work that we've done so far. So today, who we are is we are a blue technology company, really with a strong foundation in spaceflight robotics. And as we'll talk about throughout the night tonight, I think is the kind of the strong coupling between the kind of problem domain of controlling robots in space or robots on other planets, and the very similarity and the challenges to doing the same type of work with robots in the sea. So moving backwards, starting from the back first, as I mentioned, I came from a NASA robotics background. And in this video is kind of really important for kind of demonstrating the kind of stuff that we were trying to do at NASA. So we were tasked with, how do you put a very complex robotic system in a remote location, most likely with horrible communication links back to operators, and do something useful. You certainly can't drive. We did a lot of work in the early 2000s or late 1990s, early 2000s, in trying to do virtual reality control and teleoperated control. And I'll play that again while I'm talking. And found that those technologies, that kind of direct drive technology, is incredibly limited, even with the smallest amounts of time delay in the communication link between the operator and robot. In fact, I think if you're a gamer or player who plays video games, this is very well known to you. Any kind of lag or latency can really disrupt the experience and enjoyment of those kinds of systems. But same thing for operators in a teleop or VR control of a system like this. And we measured, actually, being NASA, we measured it and found that even as much as little as a quarter of a second delay was enough to frustrate and infuriate operators. And of course, quarter second would be great if that was the round trip time delay to our nearby planets, but it's much more than that. So that was the kind of research topic that we worked on a lot at NASA. We also did a lot of work a little closer to home. Here as a video of us putting together, preparing our robot. This is R2. It's getting ready to send to the space station. I love this video because, well, for several reasons here, but we'll get to those in just a second here. But so this was the launch of that robot to the International Space Station. And even on the space station, the time delays, you would think being only 60 to 80 miles up is not that far away, but you have to hop through, whoops, sorry, went too far. Sorry, go up here again. Wouldn't be too far away, but it does have to the signals from the operator to our robot on space station have to hop through several terrestrial networks before they're allowed to be sent up to the space station. And those hops and those jumps take can take on the order of up to a half second. So again, it makes it difficult doing kind of direct drive control for those systems. And plus, the other major issue is that doing direct drive control does not really create a kind of a useful team member to help out your local astronauts, because what people want out of a robotic system, especially one designed to work alongside humans like Robonaut here was, they don't want did it again, sorry. They don't want something that takes a lot of hand-holding. They want a capable system that you can give high-level directions to, and it can perform the task on its own, or with very little input from a human operator. Too much involvement back and forth between the robot and operator, it becomes a problem. So I do like this one little bit. I tossed this in here because I think it's kind of fun. So the astronauts, they live very, very scheduled lives. If you didn't know already, they're down to the minute, when they wake up, when they go to bed, when they eat, when they exercise, is all scheduled out in great detail, because their time is quite valuable. There's a lot of things that have to accomplish throughout the day, and everything from cleaning to science experiments and what have you. So their life is quite scheduled. Every now and then the crew likes to have a little bit of fun. And so on this particular mission, when we flew our robot up to the space station, because they like to show who's really in control and who's boss. And so they like to have a little fun with the ground control teams sometimes, just to try and reiterate, who's really, even though their day may be scheduled down to the second, they like to kind of exert some control over that process. So in a particular, in this, what you'll see here, we had shipped the robot up to the space station. And I think you saw in the beginning clip there, packing that goes on, the 30 or 40 people in the room monitoring every screw that gets tightened down to make sure the robot's in the box, and ensure that everything is in order when it arrives on the space station. Well, as you'll see here, the crew in a loss of signal event right before the unpacking of our robot had a little bit of fun with us and kind of pre-unpacked the robot. And then when the signal came back, they pretended like we forgot to pack the robot. And so we thought that was kind of a good joke on their part. So they pretended like we didn't pack the robot in the first place, and sure enough, they had kind of unpacked it and put it over in the corner of the space station. So anyways, but this was a really good effort for us. Here we're demonstrating kind of first robot-human handshake in space. And then you really make it when Saturday Night Live picks up your work, and I'll let them tell a joke. So hopefully that audio came through. If it didn't, I can provide the link to the video later. Anyways, so that's kind of the background I came from, and as I mentioned, when we first kind of got into the subsea space, what really drew us to the subsea problem domain was realizing that all of those years that we had spent working on very complex robotic systems and trying to operate them really far away and in poor communication conditions, that environment is literally right in our backyard, especially being in Houston, where we're at today, where I'm at. And you don't have to go to outer space to find it. And coupled with that, there is an incredible amount of hardware subsea that needs intervention. It needs people to inspect it, to perform maintenance, and perform other operations on that hardware. Now, not too long ago, it was standard to send humans down in very, very high pressure dive suits. And in fact, in some places of the world, and sometimes they still do that today. But as the use case for robots, anything that's the 3Ds, dull, dirty, and dangerous tasks, kind of formulate what is a really good target for robotic application. People started developing robots, to go do that work that divers were doing, the very dangerous work that divers were doing to work on that hardware that's subsea. Of course, the first in this work, gained some steam, and now today there's quite a big industry of subsea robotic platforms that perform a variety of tasks. But the ones that reach out and touch the environment, the ones that actually turn a valve or take a cathodic probe measurement or inspect, do complex inspection work, all have a surface side expression, a very, very large surface side expression, a very large ship that connects, that has human operators on the ship, and then a tether that goes on down to the robot. And over that tether, they can pass power, but typically it's just a fiber optic these days. It's usually just a fiber optic link, but still sometimes power. And then the fiber optic link gives them, of course, zero latency, 4K video feedback to the operator, and allows that direct drive kind of control paradigm. And your operator is flying real time in commanding the motion of the robot. The problem with that scenario is that in the increasing effort to make things cheaper and lower cost, and providing the same service but for a lower cost, that surface side ship is a big problem, because you have to have a cook who's making spaghetti every night. You have to have a large support crew and support staff to support 24-hour operations for your operators, for your robot team operators. And so typical crew sizes are on the order of about 24 people, and then you need a boat to house all of them. So you have a large boat and large fuel costs, and all these things kind of snowball together. So we looked at this problem and we said, well, if we can just cut the tether, then you don't need the surface expression anymore, or at least in the near term, you could greatly reduce the footprint of the surface expression, the ship. You could have a much smaller staff. And then so as we kind of dove into this problem some more, we realized again, like I was saying earlier, that a lot of the problems that we were working on when we were at NASA really apply in this domain as well, because we want a robot that can work efficiently and not require all of the commands and every little detail the robot does to be conveyed by a human operator. We'd like the robot to be able to have the capacity to do that itself. So, we set on this quest to kind of reinvent what was possible with ocean robotics, and came up with a few different products along the way. So the first one here is Aquanaut. This was really the where we first started off our development effort, and it's at the robotic platform, or at the core of the robotic platform. So Aquanaut was designed to, I'll play a video here. It should not have audio. It was designed to be delivered from a very small topside vessel in comparison to standard standard platforms, or be launched from shore and able to travel long distances. Then when it gets to where it's going, here we're showing it docking to a subsea docking station, but you'll see later in the video, when it gets to where it's going, it can open up and reveal manipulators that can do the work that's necessary. Again, taking a measurement or turning a valve or what have you. This was unique because it kind of combined two kind of standard morphologies in underwater robotics. Today there exists, you have your long kind of torpedo-shaped robots that have cameras on them, and we call those AUVs, autonomous underwater vehicles, and those can swim around, take pictures of things, but they can't reach out and touch the environment because they have no manipulators on them. That's one class of vehicles today, and those things do operate autonomously. And then on the other side of the spectrum, you have what's called ROVs, or remotely operated vehicles, and those are the at the smallest size, the size of about a refrigerator, but they get much bigger, about the size of a room, and like a two-story room. And those things have manipulators on them, and those things are what's tethered to a topside vessel. So we tried to kind of combine the best of both worlds, the kind of torpedo-shaped AUVs with the kind of refrigerator-sized ROVs, and kind of marry the best of both worlds to achieve the objectives of both. So that's where we started out. This is actually what's in the video here is what we call Mark II. Mark II is we started with Mark I. Mark I, you'll see in some videos later on, was our prototype unit, and Mark II is what we're going to offer commercial services to the energy market with. And it is currently in production at a partner company up in Canada, and will be rolling off the assembly line. Actually, the first one in this Q1 of this year, and then go through, of course, commissioning, qualification tests, and we'll be out in service later this year. So that's where we started, and I think we've been developing this technology now for the better part of about 4 years or so, and have come quite far, and we'll have some videos towards the end kind of show off some of the autonomous behaviors that we've developed, to give you a sample of that. Hydronaut, again, Aquanaut can travel long distances, and it's when the arms are stowed, providing kind of efficient travel through water. But for really long transits, we have also invested in the development of a surface vessel, autonomous surface vessel. And so what you're seeing here is, again, kind of just like Mark 1, the first prototype unit with Aquanaut, we started with a standard vessel and converted that for our uses as a kind of a mule platform to use for testing. But the operational scenario here is that for really long transits or really long distances offshore, we would use Aquanaut married to the back of Hydronaut, and Hydronaut would transit out to location, drop off Aquanaut, and then provide the really kind of function at that point after transiting as a relay beacon, bridging the air-water communication interface and providing that information back. Just like the Mark II units, our second version of Hydronauts are being custom built out of a shipyard out of the UK. And those, again, will be married up with Mark II, Aquanaut Mark II, the first part or middle part of this year. Initially, Hydronaut will be a crewed vessel, but only a crew size of 6, which is a significant reduction, again, from the typical crew sizes of about 24 on ROV vessels. But then as we, again, gain confidence in the autonomous surface vessel behavior, we have plans to then step that crew size reduction from 6 to 4, and then ultimately to 0. And then the two systems will only be remotely monitored from shore-based operation centers. And then finally, the Olympic arm. So one of the things that we realized, kind of stumbled into, and by chance, these are always kind of these things you don't really anticipate when you first set out on a development project, is that we were solving a very important problem to the industry that we didn't really know we were solving. And that is that traditional ROVs, the remotely operated vehicles, one of the last remaining hydraulic components on those vehicles are the arms themselves. And hydraulic is great. It provides really, really great force generation capabilities, and they can be very, very strong. However, due to the world's interest in kind of awareness of environmental issues, the industry is moving away from hydraulic systems. In Europe, for instance, it's a reportable event for every little drop of hydraulic fluid that a hydraulic system leaks into the ocean. And furthermore, at depth, at very, very deep depths, the hydraulic systems begin to lose their performance capability because it becomes very difficult to keep the pressures that are required to generate the force for these systems at very deep depths. And of course, the industry is interested in going deeper and deeper and deeper. What had not been developed, however, though, was electric work class underwater manipulators. And we, without really kind of knowing that we were solving this problem, had set out to develop a fully electric robotic vehicle, not just the manipulators, but just a fully electric robotic vehicle. And we did. And then people were like, hey, those arms, they're fully electric, right? And we're like, yeah. And they're like, that's great. We would love to have some. So we took, again, what was on Mark I, the Aquanaut Mark I vehicle, those arms, the lessons we learned from them, and rolled that into a commercial production quality fully electric arm, which is the Olympic arm here. And this is built in, we are, again, 2023 is hopefully going to be a very big year for us. We're looking to sell these to some customers that we have interested this year. So those are the 3 main products that we've developed, and then are all around this kind of this vision of doing work subsea. So switching gears a little bit, I've kind of touched on this a little bit as we've gone along. And autonomy is, for us, of course, is very, very important. For the remotely operated vehicles that I've discussed previously, autonomy is not important because you don't need it. You have a human operator connected by a fiber optic high-speed data link. You essentially have connected to your robot a water-cooled supercomputer, aka the human brain, who is making judgment calls on what needs to be done at any given second, with again in getting all the data that they need to make that decision. When you cut that tether, you are now subject to the physics of water, and trying to push information through water is very difficult. It is the great absorber of almost every spectra of energy that's out there. And really the only thing left is, sonar, and sonar, of course, has a fundamental speed limit, just like light, but light does. And there's a fundamental speed limit to the movement of sound through water. And that provides kind of the upper bounds for how fast you can kind of pass information back and forth between objects subsea. Certainly there is other technologies like optical, and over short distances, relatively speaking, short distances, you can get some higher bandwidth connections wirelessly via optical technologies. But you're limited to the range of tens of meters. Not you certainly can't communicate over kilometers with optical system. And for us, it was very important to be able to communicate over the distances of kilometers to our robot. If you think about the deployment again of an aquanaut from a hydronaut vessel, the operating depths that most subsea hardware is at is something around 3,000 meters or less, and an optical system just certainly wouldn't work at those, to bridge those depths, those distances. So what are you left with? Well, at that point, you have one of two options. You can either keep your system, your robotic system, quite incapable, and have it heavily rely on inputs from a human operator. And much like kind of the early rovers that we've sent for exploration of other planets like Mars, and those systems were systems where the robots themselves were not all that capable. So if they knew enough, for instance, if they saw a rock that they didn't think that they could get around or drive over, they would just stop. And in fact, and so mission operators would sit there and plan, okay, hey, we want to drive 500 meters forward. And then they would program in 500 meters forward and go to sleep and wake up the next day to see what happened. And lo and behold, the robot drove forward a few meters, saw something that it wasn't, it doesn't really matter if it was a rock or a shadow. The robot stopped, and they had to, all right, it's tell it to drive around and then drive forward another 500 meters. So that's an example of a system that's not very capable and does not have a lot of onboard capacities to kind of deal with unknowns or uncertainties from its environment, from its sensors. But you can go that route if you have if you're not really concerned with the kind of time efficiency of the operation. And for the case of the NASA robots on other planets, the early NASA robots on other planets, that's a trade that they're willing to make. They said, look, we don't want to take a risk, because if something goes wrong and it makes the wrong decision, either we don't have the time to do the required verification testing to ensure that all edge cases are found and that it will always make the right decision, or we simply can we will use the time to replan, and we'll just come back the next day and come back the next day. We'll just build enough time and battery life into the system such that we can still get useful work out of the system. And so that's one option. You can kind of go down, you can develop a relatively not smart system and rely on very intensive back and forth with the human operator. Or you go the other approach and you build in autonomy, which I like to call capacity, capability into the system, where it can use its own onboard capabilities to deal with the moment by moment, second by second, or maybe minute by minute, or maybe hour by hour decisions that it needs to make, depending on how autonomous you want to go. To me, autonomy is really more of a measure of how long something on a time scale, how long something can work in an environment without requiring any external inputs and to correct its action or give it new tasks to go do. So and that gives you kind of a scale on which then you need to then your communication link to the robot needs to then support. So for us, when we worked on robots, some of the humanoid robots at NASA, we were shooting for the ability where the operator, the operator could only would be required to kind of give high level direction to the robot, and not have the robot necessarily understand everything that it needs to do a task, but not be such a burden to the operator where the operator became annoyed by or frustrated by the robot because we didn't want the robot coming back to it every 2 seconds saying, "Hey, I'm stuck," or "I don't understand," or what have you. And in the case of remote operators, it's a necessity. Like your communication link just simply won't support that back and forth between the human operator and the robot, and particularly when, again, for our commercial applications, our customers they're a little more tolerant of the kind of time efficiency of our operations compared to what they're used to, being the kind of fiber optically connected platforms, but they're not willing to wait days and days and days for an operation to be completed, like they can tolerate on, say, like a NASA mission for some of the rovers on Mars. Again, they're willing to, they okay with maybe a 50% increase or a 25% increase in the time it takes to do an operation, but they're not waiting days and days and days for something to be resolved, especially if it's something that's important to them. So in those cases, those things require the system to be capable enough to make decisions on its own, and only be driven by, again, kind of high level directives that the operator specifies. So in this video is a kind of example of some of that. So I mentioned Mark 1, the Aquanaut Mark 1 vehicle. This is that vehicle. Looks completely different than Mark 2. Like all good engineers, we learned a lot of lessons on design and layout of things. So it looks different, but it functionally is the same. Has the same capability to kind of fold up into a, like I say, we built the world's first transformer. If you're a child of the 80s, you know what I'm talking about. So it has the same same basic morphology where it can open up, reveal some manipulators. It can fold those manipulators back and close up into a more hydrodynamically efficient shape. But in this video, what you're going to see is kind of combination of both kind of live video from a external ROV, little kind of mini pool ROV, that's kind of taking a God's eye view of the situation, as well as some of the information that the operator, some of the information that the robot sees, not necessarily what the operator sees, as it does a task. And the inputs to this task are really kind of that high level direction that I was talking about before. So in this task, what the robot's going to do is in the lower right hand corner, there's a tool. I'm not sure if you can see my cursor. There's a tool over off the pipe down there. And the task for the robot is to place that tool on top of the pipe that's in the foreground, lower right foreground of the image. And all that's been specified to the robot is that the tool needs to be on the pipe. And then the robot then figures everything else out. It figures out, number one, where the tool is, how to grasp the tool, where to put the robot, where to put itself in order to grasp the tool correctly, drives itself there, manages all of its motions by itself. There's no operator providing direct drive controls to this thing while it's doing it. Picks up the tool, finds where the pipe is, locates where the pipe is, and understands then how to put the tool on the pipe, and then executes all the motions necessary. So I'll play the video and talk through some highlights here. So that was, first part was, again, the external view. Here's what the robot is seeing. We do have a fiber link to the robot while it's doing this for debugging purposes. And so here it's determined a plan for where to place itself in order to move over and to put the tool on the pipe. It's already the green overlay is what it thinks where the pipe was at, and also where the tool was at, and then it goes and executes the motion. So this kind of interaction with the system, and then here's the same operation now from the point of view of the pool camera, without the additional overlays that we saw earlier. So again, this kind of operation is supported by an acoustic communications link to the robot, because it does not require high frequency communication with the robot in order to perform this operation. In this part of the video now, we're going to do the opposite. We're going to go take the tool off the pipe and move it off to the side. But the same basic behaviors and perception algorithms are running during this operation. Again, it has to figure out where the tool is, plans a location for where to place itself in order to execute the grasp, executes the grasp, and then removes the tool from the pipe. Okay. I think that's it for now. Let me just make sure I have, oops. Yep. I think that summarizes what I want to cover, and would, at this point, love to try to open up for questions and discussion.
Outstanding. So I'll get us started, and then as a reminder, if you have questions, go ahead and put the hand raise icon up. I see we got a couple. So, all right. What are some of the pressing challenges you're seeing right now in maritime subsurface platforms that could use some attention, say at the graduate education level? What are some things that maybe students like the ones that you're meeting here with tonight could be looking at for projects, and whether it's some sort of crowdsourcing type engagement, or just maybe something to look at kind of high level analysis? Where's some benefit there?
Okay, yeah, that's a great question. So we spend a lot of time with the we spend a good deal of time in the kind of the behavior design of the robot, and specifically in the what I would call kind of the conditions under which the robot decides to do, say, either A or B, and a lot of that conditional kind of logic, if you will, is backed up by, in some cases, by machine learning and other techniques in order to kind of make sense of all of the very high dimensional perception information that the robot has access to. Of course, robot doesn't make decisions on a pixel by pixel basis. It makes decisions on, hey, I see the object or I don't see the object. But for me, there's a lot of, I think, still interesting work to be done in that area of, when things don't go according to plan, When you don't, for instance, get the detection that the robot doesn't see the pipe the first time, or doesn't get a good pose estimate of the object that it's trying to mate with, for instance, and then dealing then with that unexpected outcome. I mean, it's when you're kind of laying this stuff out for the first time, you're always, I think humans just by nature are inherently optimistic, and they really only kind of think through the the positive path through the problem, right? So you're like, all right, first thing I got to do, the robot's got to recognize the pipe, then it's got to like determine the pose of the pipe, then it's got to do this and this and this and this and this and this. And that's a lot of steps that have to all go right. And we have tools for dealing with that kind of those off nominal situations. But I think in general, just one area of interest would be better tools for kind of managing that kind of state space and that decision space, and really just tools to help support laying those out, doing the analysis on that space, making sure that you catch the edge cases, because one of the real challenges of this development is testing. Testing is is exorbitantly expensive, because you do have to take a boat out. If you're doing really high fidelity testing, you have to take a boat out. You have to have crew and support staff to go do that testing, and the costs get very, very expensive very, very quickly. Of course, there are things like simulation, and simulation is great in certain cases, but simulation is one of those things that people like to say, it's doomed to succeed, right? Because it doesn't always capture all the nuances of the real world, or like the seal swimming in front of your cameras, or the school of fish that came by and fooled your perception system, or the turbidity that kind of got spun up and clouded your vision for a second due to your thruster wash. So there's a lot of stuff that does not get captured in simulation. It can be an effective initial tool, but there's a lot of other edge cases it does not catch. So I a little bit long-winded answer, but I think there's some a healthy amount of work in kind of that area of testing and reliability, and trying to find ways to gain confidence in the verification and validation of autonomous systems.
Excellent. I see we have a lot of folks chomping at the bit, so we'll get right into the student questions. I believe David was first.
Yes, sir. Hey, I got a question. You were talking about with the hydronaut being remotely operated, shore-based. Just wondering, what kind of challenges have you had with obstacle avoidance with that surface platform, and how have you addressed that situation?
Yeah, so that is kind of the general area of surface navigation. It can be a very challenging problem. I will be honest with you, we have not dealt directly with that problem, only because at least in that particular domain, we have relied more heavily on some kind of established partners who have already got a good head start in specifically in autonomous surface vessel design and development. But I am aware of the problems, because the sensing is difficult, because you're on it definitely requires like a multimodal approach where you need a combination of radar or LiDAR, some sort of kind of point source that can reach out quite far to kind of see past where cameras can't see, but then you also need the information cameras can provide in terms of the details that just can't be seen by radar or LiDAR systems. And so the right solution it definitely deserves like a multimodal approach in order to kind of first identify the obstacles. And then there's a whole kind of problem domain in terms of COLREG. If you're familiar with COLREGs, kind of the rules of the ocean, of navigation on the ocean, and building autonomous systems that are aware of those kind of rules of the road, if you will, much like is being faced in the autonomous car domain. There's rules for how to, traffic rules that, everyone abides by when you're operating on a road. And those autonomous cars have to be aware of those rules and follow those rules and kind of be, good players in that game of transportation. Same thing on navigation on the surface and for ocean going vessels. And so you have to build autonomous systems that are then aware of that space of kind of preset rules and regulations. So COLREG aware autonomy is a kind of a very hot area in the space of surface autonomous surface vessel navigation.
Excellent. I believe Jason is next.
Hi, this is Jason. So I wanted to say thank you for doing this and for the presentation. It's super cool technology. Yeah. I have a lot of questions, but obviously I'll make it short to one. That way I don't take up too much time. But the question I had is for your communication link that you guys are piping through sonar. Are you communicating like detailed tasks? Or are you like giving a basic signal frequency to a pre-programmed response?
Yeah, that's a great question. So yeah, we when we communicate acoustically, so obviously the robot provides some basic status back to the operator, kind of basic heartbeat style information to kind of, so that we know that the system's still there, still functioning, still alive. That's kind of the feedback we get. And if it's executing a behavior, we know what behaviors it has, what kind of capacities or capabilities it has available to it. And so we have kind of a simple coded system so we know what it's currently doing at a high level. Now we don't have every detailed information, super detailed information, but we kind of have a general understanding of what the vehicle is doing. In terms of a statement of what we want the robot to do, again, it kind of follows the same basic approach where the behaviors that it's executing are parameterized by in most cases, they are kind of parameterized by the activity that we wanted to do. So for instance, like when we go pick up an object, there is a behavior dedicated to picking up the object, and in a general sense, for most cases, that one behavior works for most use cases, whether it's picking up this tool or that tool off the seafloor. And so what the operator does, the operator gets back some situational awareness from the vehicle's surroundings, because we can ask it to say, hey, send us back some information about your surroundings. And we've worked quite a bit on making as much use of that poor comms link as we can. So we've spent some time on compressing images as well as point cloud information to kind of get a 3D awareness of the environment. And then the operator can kind of work with that in a kind of asynchronous fashion, work with that data once it's transferred back to the vehicle, and can then kind of specify, all right, either in an image, if it's relevant to kind of click on something in an image, or if it's or in the kind of 3D point cloud data that gets sent back, can click on something to say, all right, this is the thing I want you to go look at, or this is the thing I want you to go pick up. And then of course the robot, we send that information, that kind of click really essentially is we know where that click was where that click was taken, and in terms of the data space sent back by the robot. We send that back down to the robot, and of course the robot has access to a lot more data than we have, and can register where the operator intent was in its own local data set, and then kind of connect the dots in terms of, okay, we're doing a inspection operation. I was told to inspect this point over here, and then it knows then, okay, I know how to do inspections, and it kind of carries on with the activity. In cases where there's some uncertainty, or sorry, for objects, like picking up objects, it's a little bit different, but in the inspection, it has kind of a preset library of objects it knows how to interact with. And the robot can detect objects itself. And then it will query back to the user, say, hey, I think I saw a pipe over here. The operator confirms that, yeah, no, that was the pipe. And then the robot then knows how to interact with that pipe because it's a preset object it knows how to deal with ahead of time. So that's kind of give you some example of the kind of back and forth that between the operator and robot.
Great. Ethan.
Hello, sir. Thank you for taking the time and doing this discussion with us, first of all. Next, so I'm explosive ordnance disposal for the Navy, so I'm very familiar with the underwater clearance of like MCM missions, mine countermeasures, things like that. So I have a two-part question. The first one would be, I guess you kind of hit it on the last, but the first question would be, have you thought about doing any programming for a mine countermeasure mission for the Aquanaut to be able to identify and locate in the open water and be able to relay that information possibly for like a clearance mission for a carrier or something like that?
Yes. In fact, we have, I think it was mentioned in my introduction, I've done, before becoming CTO, I was principal investigator on a lot of our defense related work. So Nauticus Robotics has been, I don't know quite percentage wise, but we've had 1 foot squarely in the defense world and 1 foot squarely in the commercial world. And I've talked mostly today about our commercial endeavors. But yeah, absolutely. Mine countermeasure missions are the types of tasks that we do commercially and, well, I should say aspire to do commercially, that we will be doing shortly with the Mark II units commercially, have direct parallels to a lot of the activities that are of interest in the defense space. And yes, absolutely, whether it's inspection, detection, intervention by trying to neutralize explosive ordinances, has been things that we've looked at with our defense sponsors, and there has been a lot of development in that space, and it's something that we're really excited to work on. For me personally, it's something that our company is engaged with an awful lot, but it's for me on just a purely personal level, it's something that I'm been very honored to work on and be a part of.
Oh, definitely. It'll make my job a lot easier and safer as well.
Yeah.
The second question would be, if you do have that, since you do have that capability or working towards that capability, will you have communication links between multiple robots or AUVs? Like another REMIS system currently that we're using has that capability where it can speak to a different REMIS system. But would this have that as well? Yeah,
that is definitely, it's not something we have today, but it's a, again, kind of a personal belief of mine is that just in general, I think that the heterogeneous teams of robotic systems, kind of something like Aquanaut, where it's a very complex, high dollar, kind of very complex machine, high dollar amount vehicle, combined with like smaller, cheaper, maybe purpose-built machines. That kind of heterogeneous fleet approach is, I think, in general, like for a lot of robotic applications, I think is really where I know there's lots of research in that area, and is an area that is a solution approach that I think works for a lot of would work for a lot of problems. Some systems, because you don't, you don't always want to like use kind of the big expensive machine to do all the tasks, where maybe it's something a smaller, possibly disposable vehicle can do some tasks better, or if it's in certain situations, it might be better to sacrifice another vehicle. So I think that as a general approach, I think kind of heterogeneous teams are really the kind of if I was able to kind of direct all research dollars towards problems, like that would be kind of the approach I would take to lots of applications where we want to apply robotic technology to remove operators for whatever reason, for danger or for the other reasons that you might want to apply robots to systems. Because I think you get a lot of inherent, or I think you get the ability to gain a lot of inherent robustness to the completion of the tasks that you want to get at the end of the day.
Perfect. Thank you very much. I really appreciate it. Thank you.
Next up, Gerald.
Hi, John. First of all, again, thank you for your presentation. It was fantastic. So I'm a bit out of my comfort zone with maritime systems, but my question is I guess, just trying to relate your system to what I know with flying airplanes. And so flying drones, we have lost comm procedures. What it does if it loses comms, if it loses GPS, it has certain pre-programmed functions. So does your system have that sort of pre-programming? And are there any situations where, say, it might not be what you want to have the thing surface in a particular location or something like that?
Yes, absolutely. Again, that gets back to something I kind of touched on a little bit ago, which was that kind of how the robot behaves in an off-nominal situation is really important. And I kind of the examples I used were kind of more task-based, like doesn't see the object you intended to see, or something else happens. But that same autonomy architecture, that the tools that we use to build those autonomous behaviors works the same for situations like loss of comm. And you're absolutely right. There are we today commercially, for our commercial systems, we use some relatively simple behaviors where if it doesn't hear back from the operator in a timely fashion, then it knows to kind of just wait around. Maybe it will get the signal back, and then if it persists, then it will just start executing a return to recovery position, like a pre-pro. We know where we launch, and so we know where we can recover at as well. And there's a variety of other conditions which can happen. Maybe it's not necessarily loss of comms to the system, but maybe it's the vehicle has some other kind of sensor malfunction or onboard malfunction, and dealing with all of those conditions it's a very, very large space to kind of noodle through if you're a human, and so exploring that space of situations efficiently to build robustness into your system is really where I talked about that earlier, but it's one of those things that really is a difficult problem to suss out, and it's just too expensive to just test in the real world to find all of them. And there are some really interesting there's some really good work that's being done out there in this domain of trying to build robust systems. And one other point you made too is absolutely, there's certain, especially in the defense applications, it is different behaviors that we have for if the vehicle's lost for whatever reason, but those can be configured ahead of time based in kind of in that autonomy behaviors that we have developed today.
Awesome. Thank you.
All right, Anthony.
Yes, hello. Thanks again for your presentation. My question is, you talked about the example you gave with your robot was putting a tool on a pipe. So that got me thinking, is that robot pre-programmed task specific, or can you program it autonomously to perform multiple tasks at one time? Follow-up question, if it is single task, hold on a second. Sorry about that. Can you on the fly change the programming through your communications link?
Right. So one of the things that we are working on in development, so I'll say this. So we have a pretty extensive library at this point of capabilities, onboard capabilities that the robot can perform. And generally speaking, before we go out and do an activity, we effectively have a mission plan. We know that we want to go over here and do something, like maybe image some stuff, and we want to go over here and then image some stuff again. But if you see something, then like go in closer and inspect it. And then if you go inspect it and it's a certain type of object, like pick it up and move it, and then go to the third area and do something else at the third area. We can support those kinds of mission plans that have kind of that if then else type of direction from kind of some knowledge, some general knowledge about the area, or some general knowledge about the task or application. But that's an area that we've been working on a lot recently, where the conditions of the environment, the local conditions of the environment that the robot finds itself in, kind of drives the robot behavior. Like I was using in that example, where the robot, nominally knows it's just going to go inspect an area, do a small survey of an area. But then while it's surveying, if it finds some object, it knows that, okay, I found an object, but the object is not, and it needs to be in my payload bay, but it's not in my payload bay currently. And so it knows that, okay, well, to make that a reality, like I need to go closer and inspect, because I don't know how to pick it up yet. And it kind of continues down this chain of events that need to occur in order for it to realize kind of an end goal application of this object needs to be in my payload bay. And it kind of knows how to, by itself, kind of piece together those sub behaviors or the sub capabilities in order to achieve a final objective. That's some of the development work that we've been working on recently.
Okay, thank you for the answer. I appreciate it.
Yep.
All right, Sam.
Yeah, good evening. You guys have me limit, Charlie?
Yeah.
All right, good stuff. I have 2 little kids, so I will try not to call your vessel an octonaut.
I'm very familiar.
Yeah, it was funny because I had guests this week and they kept calling it aquanauts when we were watching the show, so now I'm super confused. But anyway, I noticed in the early part of the vessel, or the early part of the video, you had it traveling long distances on its own underwater. About how far is that, and what means of navigation are you using?
Yeah, so for our commercial applications, the range is, I don't know what right off the top of my head, I don't have the total range of the Aquanaut vehicle itself, the Mark II unit, but it's meant to be on the order of about 10 kilometers, I believe, and be able to do some useful work and come back. I don't remember what the ultimate range number is, if you didn't care about doing any kind of useful work when you got there. But in our commercial applications, where surface expression is not an issue, the vehicle has on board GPS and can come to the surface to gain a GPS fix. And then underwater, it then has kind of the standard fare of underwater navigational systems, laser ring gyro and DVL systems, Doppler velocity log systems, kind of measure speed over ground. And those are all, and of course, depth sensors and other systems. They're all fused together to provide a pretty decent inertial estimate of where the vehicle is, especially when combined with the DVL input. Without DVL input, certainly if you're just inertial only, the uncertainty can grow pretty quickly. But with DVL input, you can with bottom lock from that sensor, you can maintain a pretty good understanding of where you're at. Then when it gets on site locally to a job, it can use what's called, if you're familiar, SLAM, or simultaneous localization and mapping techniques, to kind of build up a local area map of where it's at. And that uses a combination of both the INS inertial information as well as visual features and sonar features from the environment to kind of know where it is locally within this kind of 3D space where it's operating for a given task. Hope that answers some of your question.
No, I appreciate it. Thank you.
Mm-hmm.
Kevin?
Good evening, Doctor. I appreciate this.
Mm-hmm.
So my question is coming from a communications background, and everybody always wants more bandwidth. And I know that, like, you know, if we had infinite bandwidth, these autonomous robots under the sea would be rebuilding Atlantis. But I guess my question is, like, what exactly, and I apologize if I missed it, but what exactly is like the current bandwidth in terms of, let's say, data rate, and what would be like the next realistic step in terms of achieving more bandwidth, and what would that accomplish in terms of the capabilities of your systems?
Yeah. So that's there is some research going on and some development work going on in trying to squeeze more juice out of the lemon that is acoustic communications underwater. Like I said earlier, there really is, you're really kind of butting up against physics, because you're really at the mercy, again, ignoring for the moment kind of close range communications underwater, where again, optical technologies are, you know, germane. And for those optical technologies, again, it's range dependent, but like you can achieve something on the order of megabit to maybe 10 megabit per second, again, depending on range, kind of data rates. Acoustically, typical systems today are effectively on, because it doesn't really get measured quite this way, but a kind of effective bandwidth is something on the order of 30 kilobits per second, not bytes, but kilobits per second. And it's there is some research and development where some teams of people have pushed that as far as 100, maybe up to about the 100, 120 kilobits per second. But that's really kind of high-end technology. And it also depends on whether you're talking vertical channel, so kind of straight up and down in the water column, or horizontal channel. Because in the medium of the ocean, there are all manners of environmental conditions that affect your effective bandwidth. And you know, everything from differences in salinity to differences in temperature can cause echoes and bounce backs and reverberations. So you know, it depends on whether you're talking horizontal or vertical channel. But in that specifically one group I'm thinking of, they have achieved about 100 kilobits per second in kind of vertical channel tests with their technology, but only doing so with you know, kind of using kind of multispectral approaches, simultaneously kind of broadcasting over multiple spectra. but so there is still some juice people are trying to squeeze out of it, but I don't know how much more you can get, because they are kind of running up into physics, and laws of physics can't easily be rewritten. So that's kind of the ranges of where technology is today.
Hey, thank you, sir. I appreciate that.
Mhm.
All right, Ryan.
Good evening, sir. Thank you for your presentation. I have a two-part question. First and foremost, when you guys operate, do you have to have a notice to mariners? And then my second part, as far as your data transfer, is there any sort of protection for the data you're sending to and from the vessel in your vehicle? Can that be intercepted by a third party, or something send out a signal that's more powerful to interrupt what you're doing? Or is that something that you're looking into currently?
Good question. So the first part, no, there's not. When we're operating commercially around, there's not necessarily a notice to mariners, but there is of course, agreements and understanding, safety paperwork and all kinds of stuff that we have to go through with the owners of the equipment that we are going to be working with. In fact, that is, there's a lot of kind of the progression of work with offshore operators, like your Exxons or your Chevrons or your Shells, that kind of thing. Have to go through pilot programs to kind of, so they understand that you're kind of a safe group to work with, and they understand your technology. So that's kind of how a lot of work with them progresses, is through kind of pilot programs that we're currently engaged with some folks. And so they own the equipment, and they won't let you near the equipment if they suspect that you don't have your system well understood and well controlled. The second question, is information encrypted or protected? Again, on the commercial side, no, not explicitly. Can it be interfered with? Yes, it could be, and that's why our defense projects don't like communication whatsoever with the vehicle. Their interests are more on the side of full autonomy capabilities that do not require surface expression or do not require communication with the vehicle, to eliminate that possibility as a vector of attack or interference.
Thank you for the clarification.
Mm-hmm.
Joe.
Okay, thank you for the presentation, Doctor. I wanted to follow up on Anthony's excellent question about the Aquanaut and its ability to modify complex mechanical problem solving on task. Is there any type of operation solutions that maybe involves an initial troubleshooting mission whereby they get to the object in the pipe, maybe it's more complicated than placing a tool on it, it needs to screw a cap onto the pipe. Then where there would be an initial sortie that does the troubleshooting and then reprogramming the Aquanaut to send it out on a subsequent mission to do a more high-level mechanical tasking.
Yep, great question. So that is exactly the kind of direction we're trying to get to, in our current development work to get to. So today, let's take the example of kind of pipe inspection, non-destructive testing, or what they call NDT testing of pipes. Today, that involves a minimum of at least 2, maybe 3, depending on how you want to cut it, but 2 primary steps. The first step is that, and this happens for every pipeline, and there's miles and miles and miles and miles of pipeline subsea all across the world. And so for every pipeline that's out there, those have to be inspected on a kind of a regular basis. And they do kind of statistically. So they'll pick a few locations along a pipe and try to then gauge, the overall health of the pipe. But before they go do the kind of NDT testing of the pipe, they will send one vessel in ROV. This is current approach. They'll send one vessel and one ROV to go kind of clean the area. They'll clean the pipe and any kind of surface buildup on the pipe to kind of prep it for subsequent inspection. And then that boat will leave, and a new boat will come out with a different ROV and possibly the tool, like similar to the tool you saw in the video. And that crew's job will then be go put the specialized tool on the pipe, make some measurements, and report back what happened. And so what the kind of autonomous capability we're working on today, it's not ready for commercial use yet, but it's been something that we've been working on, is that understanding that step A needs to be done before step B, and step A might be something like, first clean the surface, and then you can apply your sensor measurement to that surface now that it's been prepared. And there's kind of a domain of research that is out there that kind of has systems to kind of deal with this problem. It's kind of generally known as like task planning problems. And it's actually been kind of a heavily researched area, at least since the early 90s, maybe mid 90s, where they actually developed competitions where researchers from around the world would be kind of at the beginning of some period would be given a kind of a problem statement, and then they would get to show up so many months later with their cool algorithm that would try to solve this kind of multi-step, or what other people call like long horizon, multi-step or long horizon planning problems that might require multiple steps in order to achieve a solution. And so we are using those technologies from that domain to try and endow. So our commercial partners are very, very interested in that, because you can imagine that if they could pay for one vessel to come out and do the job, as opposed to two vessels and two crews to come out and do the job, they are all about that and they would love that. So yeah, that is of great interest to them. And of course, on the defense side, there's also a lot of interest there, because then you would have a system that can do more complex multi-step tasks without the multiple round trips to do something.
Very good. Thank you.
Mm-hmm.
George, you're up. And just to let you know, we do have a couple in the chat that I'll read out
Sure.
after Lindsay.
All right. Good evening, sir. Thanks for your presentation. Can you guys hear me? Yes.
Mm-hmm.
Perfect. I wanted to ask a question about the hydronaut.
Mm-hmm.
During your presentation, you were talking about the surface autonomous vehicle and crewing it initially, stepping down from six to 4 to none. Does that vessel, will it carry the Aquanaut on board, or is it towing it? You mentioned it, but I wasn't quite sure. I wasn't understanding how it was connected.
Yes, it is carried on board on the back deck of the vessel. I kind of skipped over that part maybe in the video when I showed it. So it's carried in a basket, what we call a basket, where and that basket is then deployed or kind of scooted off the back of the vessel, then dropped down, and then the Aquanaut vehicle can then egress from that basket, go do an operation, and then also be recovered in the same manner. So yes, it's carried on the back.
Okay, thank you very much.
Mm-hmm.
All right, Lindsay.
Hello, everyone. Can you guys hear me okay?
Yep.
Awesome. Well, thank you again. I'm really new to unmanned marine vehicles, so this whole thing I'm just kind of absorbing. I did have some questions because I don't want to be redundant to some of the awesome questions that have been asked, but you made a point that I think is really important in the unmanned field, which is it takes people to be unmanned. And you mentioned that it takes people for maintenance, for inspection. And so my question is regarding just your fleet, the fact that they are engineered for this particular task. And I would imagine that they're pretty innovative within their field. How do you guys handle, I guess, your seaworthiness program, so to speak? So change orders and maintenance, and how do you guys manage that whole program to keep your fleet operational given the circumstances it operates in?
Yep, that's a great question. So it does take a village. It does take a village to build a robot, and that's always been the case through my whole career. So yeah, no, we have I think a stellar. We have first of all, we have a stellar engineering group that does. We have at Nauticus, we've got every discipline kind of represented: computer science, mechanical engineering, electrical engineering, and to build and design these systems, it takes robotics is a multidisciplinary field. You can't possibly know everything that's needed to know to build and field these systems. So it takes quite a few skill sets to do that. And then in addition to our engineering team, we have I think a world-class mission services group. The mission services group is responsible for that real-time maintenance and operation of our assets, and it's composed of when we're crewed, when we're in a crewed vessel like Hydronaut, that group is the ship captains and the first mates and the robot operators and the technician staff and the maintenance crew, and so it does take a sizable crew of people to keep these things running and operational, and and enables smooth operation for us. We currently have the one Mark I prototype, that the Mark I Aquanaut that's shown here in this picture on the back deck of a vessel, not Hydronaut, but another vessel of opportunity that we used for some testing earlier this year, actually. We also have a defense variant of the Aquanaut vehicle that we currently maintain and are doing testing with, as well as the Olympic arm that I showed earlier. And in addition to that, some other kind of smaller projects on other surrogate vehicles. And so all that together, and that's even before the Mark IIs and the second generation Hydronauts kind of roll off the assembly line. So we already have our hands quite busy with maintaining and operating this system of vehicles, and it will only get we only get busier as the new units kind of roll off the assembly line.
No, that's helpful, because I imagine that's probably also a benefit you provide to your customers beyond just the asset, is the maintenance and monitoring feature.
Yeah, that's right. In fact, yeah, and I will add one more thing to that. So I didn't make this clear in the beginning, but commercially, what we provide is not the vehicle. Like, we don't sell, the Olympic arm is the exception, but we don't sell Aquanauts to people. We don't sell Hydronauts to people. What we sell to people, what people are interested in typically, is the service that they provide. So we sell the service, but Nauticus owns and operates the Aquanauts and the Hydronauts. We can do so. We can sell that service at a lower cost point because we don't require as large of a kind of operational footprint as competitors do. So I'm going to make that
Thank you.
distinction. Yep. Mm-hmm.
Excellent. Well, I've got a couple questions from the chat. Rickard, he says, first, thank you for your presentation. He's got a multi-stage question here. Okay. How do you foresee the future in regards to autonomous subsurface navigation over long distances? Mm-hmm. And then how accurate can you repeat a waypoint such as lat long, depth and time mission today?
Yeah, so that is a very tough problem of navigation without surface expression, especially subsea. And so it is a domain that is of high particular interest on in our defense projects. And we have partnered with some external groups who are doing some really excellent work in that area. And I can't go into too much detail on that, but they are using some innovative techniques to provide effectively what you lose in aerial domains or terrestrial applications where you have, well, not always, because there are ways to deny GPS, but for typical applications, terrestrial applications, of course, you have GPS, but subsea, they are working on techniques that provide that kind of position fix, if you will, based on a variety of kind of different sources of data. So yeah, no, it's a very very hard problem, and we are kind of working with some folks who are kind of specialized in that domain on some work. It's quite interesting. In terms of our ability to with the vehicle to hit waypoints. So when we're doing surveys, I can't put the numbers in terms of maybe lat long values, but we're able to, of course, you know, the longer on our commercial vehicles, the longer you go underwater without a GPS fix, of course, even with a DVL kind of aided inertial guidance system, you're always, any inertial based system, aided or not, is going to build up error over time. And so typically we are on the order of less than a meter when we're doing kind of a survey in terms of the distance away from the desired survey track. It's typically less than probably less than 100 centimeters or less for a full survey track. But of course, the longer the bigger the survey area, or the longer the transit we got to go out to a survey, that can grow and does grow unbounded, unless you have some other way of fixing your location fix. So hope that answers the question.
I believe so.
Okay.
The next question is from Rajesh. Knowing what we know today of the capabilities of such systems, could any of these systems have helped with the location of Malaysian Airline 370?
Yeah. That is, we've had some, I don't want to give the wrong impression. We've never been contracted or never done any work to go find something like that incident. But we have had experience of trying to relocate objects that we put into the ocean. And it is, unless you've done it, it's hard to express how frustrating it can be to locate objects, even if you knew where you put them in originally. And unless you have a tracking buoy or a tracking device on the object subsea, like a USBL device, which is kind of like USBL is kind of like a subsea GPS system. But unless you have something like that, it can be infuriating to try and find something, even if you knew where you put something down, and go relocate it again, unless you have some sort of tracking device on it to relocate that object. I can only imagine how difficult it is to find something, where you don't know where it is ahead of time. I think that the only way to do better at a solution like that is through fleets, homogeneous or heterogeneous fleets of systems that can really just paralyze the search effort and search more space efficiently or quickly. Is the more assets you have looking, the faster you can kind of cover that space and find what you're looking for. But the ocean is to say it's a needle in a haystack is really underselling how hard the problem is, because how big the ocean is, and it's hard to really comprehend that unless you're tasked with doing something like that. It's really quite difficult problem.
The next question is from John Kramer. It's also a multi-part, and I believe it's coming to your perspective as someone who was working at NASA that then came into the private sector. And
yes, that's correct. That was
oh, there you go.
I wasn't sure. It's coming a little patchy, so I wasn't sure if you were going to be able to hear me from there. But yeah, one of the things I was really interested to hear was how you guys went about finding people. Once you had your design all figured out and everything was pretty much as you wanted it, how did you go about finding manufacturers that could even produce things that could survive those marine depths? Kind of the reason I asked is because I'm working on a project now that functions in lunar, is intended to function in lunar environments, and kind of has those similar really high specifications and tolerances for heat, cold, all those things. How you found those types of manufacturers who were even capable of it, and also, like you said earlier about the village, currently it's just me, and I was wondering how you actually went about finding people to work with you, and while at the same time protecting your intellectual property in case you can't afford a patent like myself.
Yeah. Yeah, I understand. So on the materials front and on the manufacturing front, we I guess we're fortunate in some ways at NASA. Well, we were certainly blessed with some very great facilities there at NASA. And we were able to, we didn't build everything ourselves. We certainly, even at NASA, we relied on, say, external vendors to do circuit board manufacturing. But we did do a lot of custom design work, and then would send out that custom design work to different fab shops or to different machine shops. Because especially when we worked on some of the humanoid robots, back in it wasn't too long ago, it was in the late 2000s. There were not a lot of commercial products available on the market that either fit in the form factor that we needed, because when you're building a humanoid robot, you're trying to shoot for a certain volume, and there's, you don't want to build like a 20-foot humanoid robot. So, the space is somewhat constrained. So things like motor drivers and such like that, things like that, we did find we had to design ourselves, because at the time, it's not really true anymore, but at the time there was not the kind of power density capable from a lot of the commercial products that we needed. So we did a lot of custom board design, multi-layered custom circuit board design that we were able to find manufacturers capable of producing those things. Mechanically, we again also have machine shops that we use quite frequently. Some of our contracts and some of our work requires kind of made in the U.S. Has made in the U.S. requirements. Others do not, and so we, depending on the work and the target application, we can either reach out internationally, and over the years, we've built up a good relationship with several machine shops and fab shops internationally, as well as some excellent facilities here in the United States. I think that that's on the manufacturing side of things. People-wise, you talk to anybody, and hiring is a problem for everybody, and it has been, not even just recently, but certainly recently with the way things went with the market, but even before COVID and all that kind of stuff, it is really challenging to find folks who are kind of top of their game in whether, again, it's in that, those different engineering disciplines, or even on the mission services side, people who are dedicated to their craft, so technically very sharp, but also are, in my book, I think one of the strongest characteristics are folks who are solution oriented, and I kind of have that real can-do attitude, try several solutions before they ask for help type people. And that is really hard to come by. It just is. And so we've been fortunate to have, a lot of the people that were core to the company when we left NASA are still with the company, which is great. We have lots of years to leverage in terms of relationships and knowing how to work with each other. But we've also grown since then and added folks to our ranks. And again, in that area, we've also been quite fortunate to hire the folks that we have. And so but it's a hard problem. It takes a lot of time and effort and interviews and all that kind of stuff to find those folks.
Outstanding.
Thank you.
Mm-hmm.
I have one last question for you.
Okay.
Does support personnel TDY with the Hydronaut?
Sorry, what was that? Does support personnel do what with the Hydronaut?
TDY, do they travel with it?
Yes. We with Hydronaut specifically, we actually it depends on the where the job is at and what the task is. So for instance, for one contract, we just sent we don't have any of the new Hydronauts built yet, but we have our kind of mule vehicle, our test vehicle that was shown in one of the videos that's operating today. And we actually just sent that vehicle out to the Florida Panhandle for some work out there. And there was a crew that, physically drove the boat over there, a small crew that physically drove the boat over there. And then the rest of the crew flew or drove, depending on whether they had to take material with them to meet the vessel at the harbor at the point of departure for that work. So generally, though, for our robots, like the robotic platforms, it always depends somewhat on the testing regimen and what we're doing for a particular job or contract. But our mission that missions services group, we cycle people in and out of the job, and we expect everybody who's part of that team to be at the same kind of level of competency in terms of working on various aspects of the system, and they go through the requisite training in order to get that level of comfort. And so we kind of a pool of people that we can kind of cycle in and out to kind of keep people fresh on. If it's only like a week job, then we're not cycling people out, of course. But if it's like several weeks long or several months long, we can cycle. We cycle people in and out there, keep them fresh.
Outstanding.
Mm-hmm.
Well, I want to thank everybody for joining us tonight, as well as a major thank you to Dr. Yamokoski for sharing his perspective and thoughts regarding this technology. It's been a very informative session, and it's helped us to gain a better understanding of the future of this field and a little more insight into subsea maritime unmanned and uncrewed system technology. That's something that we're always looking to kind of grow that exposure. And John, one of the things I think you helped really express here was just the amount of commonality that exists among domains and how examination of one can help us perhaps uncover solutions in other areas or environmental operations.
Yeah, absolutely. I just would add, back to what I said earlier, that area of building robust and verified and validated autonomous systems is applicable. That autonomy operates at a level that is it's not quite indifferent to the platform, but it operates at a level that's very high. And a lot of the details of the platform, the physical manifestation of the robotic platform at that level is somewhat abstracted away when you're operating at that level of autonomy. Sure, there's sensors and there's details of the sensors and all that kind of stuff, but once the information flows up to the decision-making layers of the autonomy, it's almost it's almost irrelevant whether you're a rover on Mars or you're a subsea robotic platform or you're a autonomous car driving down the street at that level. And so a lot of that problem area is common amongst all applications of robotics.
Outstanding. For those of you in my sections of UNSY 501 and 502, please remember to put your brief statements together and post them to the discussion area by Sunday. I should have a recording from this session, as well as a link of, I came up with a whole bunch of related resources as we were talking. I'll have those all in there. It's some good stuff. A link to the Robonaut 2, some explanations of ROV versus AUV, and what architectural viewpoint of a tethered ROV, as well as just some of the background of what we talked about with autonomy in the space environment and autonomy in relation to Colrex, and even some stuff about their dealing with inertial drift for navigation. So really just good stuff came out of this conversation. So
awesome. Yeah, there's no end of fun problems, that's for sure.
Yeah. Well, and as you guys are expanding and looking to grow, please don't forget about our students here as potential employees, in the future.
Absolutely. Yeah, we have like most companies, we have a careers page. You can apply anytime, even if there's not something that's necessarily there. It does get filtered. Good candidates do come across my desk all the time from our HR department. So absolutely, we're always looking for good, talented people. So
wonderful. Well, thank you, John, and thank you everybody for joining us. And I'm going to stick around for a couple minutes in case anybody has any questions. Otherwise, I'll see y'all in class throughout the rest of the week. Just a brief note, as I don't know if you could tell or not, I'm still getting over the flu. So
sorry about that.
Yeah. I was like just pumping the NyQuil all day to make sure I was able to be upright for today. So
understand. Well, you did a great job. I appreciate this has been awesome, and the questions that were fantastic. Thank you, everybody. It's been a pleasure.
Thank you.
All right. Bye.